All right, so this is going to be 7.1, defining acids, bases, and pH. All right, so let's go to acids, bases, and the definition that we're going to stick with is the Bronsted-Lowry definition that we talked about in the POGIL activity. The Arrhenius definition is good, but the Bronsted-Lowry is just a little bit easier to handle, and it's a little bit more all-encompassing. So based upon the Bronsted-Lowry definition, the acids that we work with are going to be defined as proton donors, and the bases are going to be defined as proton acceptors. So again, the acids are the quarterbacks, the bases are the wide receivers, or the acids are the pitchers, and the bases are the catchers. When we talk about proton, you got to remember that we're really talking about a hydrogen atom that has lost its electron, which is just a proton. So make sure that you keep that in mind. So acids are proton donors, and bases are proton acceptors. So we're going to look at kind of a difficult equation here, where we start with an acid called hydrofluoric acid on the far left. You see that it has one hydrogen and one fluorine atom right there. And we're going to add that acid to a base, and this base is going to be ammonia. And you see that the ammonia molecule right there, the trigonal pyramidal structure. And so the acid, being the proton donor, is going to give its proton to the ammonia. All right, and then if we look on the other side of the equation, now our original acid is devoid of that hydrogen. Where's that hydrogen? Well, it's right there. Okay, it's been placed on our original base. And so down here, if we look at kind of our definitions, we've got our original acid, which donates the hydrogen, and our original base, which accepts the hydrogen. But on the opposite side of the equation, we actually have another definition for an acid and for a base. And these are what we refer to as conjugate acids and conjugate base. So a conjugate base is what remains after the acid has donated its hydrogen. Because when we think about these types of reactions in chemistry, these reactions are a little bit different than the typical ones, meaning they're equilibrium reactions. So what an equilibrium reaction means is sometimes the reaction can run to the right, but sometimes the reaction itself can reverse, and it can shift back to the left. And if we think about the reaction shifting back to the left, like this, we can now classify this guy, this fluoride ion, as our base, because what's it going to do? Well, it's going to accept the hydrogen, and when it accepts the hydrogen, it will then turn into that guy over there. Okay, so we've got an acid and base that we start with, but then through this reaction we form what's called a conjugate acid and base. Okay? Those are some definitions that again the POGIL touched on, but I wanted to get down into our notes. So how do we determine acid strength? Well, you're probably familiar with pH, and pH stands for the power of hydrogen. And so the more hydrogen you have, the stronger your acid typically is. But we have to look at a pH scale to get a feeling on how pH actually works. If you look at the document here on the bottom, or the picture on the bottom, you'll notice that neutral, okay, neutral is right about there, so 7. That's neutral. As we get more acidic, we actually decrease our number. So something that's 0, has a pH of 0, is really super acidic, so it's like battery acid. That's some pretty dangerous stuff. Stuff that you have in your kitchen at home, like lemon juice and vinegar, also has a very low pH, so 1 or 2. On the flip side, if you've got something that's very basic, sometimes we call it alkaline, it's got a high alkalinity, okay? That basic material has a high pH. So if you'll notice, like ammonia, which is usually a cleaning product, it's got a pH of 12, because as the previous slide suggested, it's a base, okay? Baking soda is basic. All right, baking soda is basic. All right. So the pH concept is a logarithmic scale. I know I mentioned that word yesterday, and I got a lot of groans from everybody. But essentially, this is what they mean. So lemon juice from the scale here has a pH of 1, and battery acid has a pH of 0. So if you were to ask yourself, well, how much more acidic is battery acid than lemon juice? If you just look at these numbers, you would say, well, lemon juice is 1 more or less acidic? I don't know. But based upon the logarithmic scale, this is what it means. Battery acid, because it's got a lower number, 1 of a lower number than lemon juice, battery acid is 10 times as strong as lemon juice is. If, for instance, something had a pH of 2, so pH equals 2, then battery acid would be 100 times stronger. If something's got a pH of 3, let's go back here, fix that up. Something's got a pH equal to 3, then battery acid would be 1,000 times stronger. So you can see every single time that I increase 1, I'm actually adding another 0. And that's why the logarithmic scale is used, because it keeps our numbers nice and small and nice and convenient without having to use really huge or really small numbers. So that's one of the reasons why we use it. So we're going to have to determine some acid strengths in class, and so I'm going to kind of walk you through the process to do that. So first of all, pH. Let's say that you're given the concentration of a particular acid, and you want to know its pH. So the higher the concentration of the hydrogen ion, the lower the pH is going to eventually be. So let's take a look at a sample problem. We're going to find the pH of a sample of 0.013 molars HCl. So HCl, when it does its thing, right, it breaks down into H plus and Cl minus, and you can see that for every one of these, I get one of those. And so if I've got 0.013 of this, I also have 0.013 of that stuff as well. So if I plug that into my equation, I get the pH equals the negative log, and you'll have to find the log button on your calculator. This is log base 10, by the way. Negative log of 0.013, and if you do that appropriately, the pH of this particular sample should come out to be 1.89. 1.89. Okay? So, yep, it'd be acidic. It's less than 7, so it's certainly acidic. All right, so let's go on to the next one. Some types of acids. We have strong acids. Strong acids are going to be acids that dissociate 100%. And remember, dissociate means to break apart. Okay, I'll show a picture of that in a second. The main strong acids that we know of are HCl, HNO3, and H2SO4. And we're going to have to be comfortable with the names of these. HCl is hydrochloric acid, HNO3 is nitric acid, and H2SO4 is sulfuric acid. Weak acids dissociate less than 100%, so they don't all break apart, the molecule that is. And a very common weak acid is this one, HC2H3O2, which is more commonly known as acetic acid. So this is the acid that's in vinegar. So if you look at a picture here, if I were to ask you which one is the strong and which one is the weak, you hopefully would identify that as being the strong acid and that as being the weak acid. And the reason behind that, by the way, is that the one here on the left, you notice everything is dissociated. Everything is broken apart. So this red dude is completely separate from this purple dude. You'll notice here on the right side, a lot of them are still combined. Just that every once in a while you get one that loses its button. So that's what kind of defines that weak acid. So how about bases? It seems like we're leaving them out. So basic solutions do not typically contain many protons, many hydrogen ions. Instead, we can utilize something like POH to help us with the strength. So POH looks very familiar to pH. That's our equation. And if we ever want to convert a POH into a pH, because that's more familiar to us, the pH, we can utilize this concept. And that's that the addition of these two things, the POH and the pH of a substance, will equal the number 14. Okay, they always equal the number 14. So if we had a problem like this, find the POH of a 0.0078 molar sodium hydroxide solution, we'd probably handle it first by finding its POH. So it'd be the negative log of 0.0078. And then whatever that number would be, okay, we would plug this POH number. Let's say that comes out to be smiley face. Okay, so then we would take smiley face plus pH equals 14, and we'd solve for pH, right? So 14 minus smiley face, and in this case, smiley face, or our pH of the substance would be 11.89. And that makes sense again because 11.89 is higher than 7, which is kind of what defines on a pH scale what a base is. Okay. All right, we can also directly switch from hydrogen to hydroxide ion. We'll use this equation to do that. So in any solution, If you find the hydrogen concentration and the hydroxide concentration, you multiply those two together, you're going to get some number like 1 times 10 to the negative 14. So if I were to ask you to determine the hydroxide ion concentration of a 0.36 molar HCl solution, well, it'd look a little bit like this. You would take 0.36, you're multiplying that by, well, your unknown, which is the hydroxide ion concentration. That equals 1 times 10 to the negative 14. And if you do this appropriately, mathematically, you're going to find out that your hydroxide ion concentration is going to equal 2.78 times 10 to the negative 14. Okay? So we'll talk a little bit more in class about the importance of these numbers and where these numbers come into play. But the first idea is to get comfortable with their computation so that we can talk about them a little bit more freely. All right, that's 7.1.